Hi, let's dive into lesson 2 search problems. Before we even read the problem, let's do a little refresher on the terms of a search problem. A state space is every way that the world can be. It's essentially anything that can change, like our location or the enemy's location. That's all part of the states of the world. A successor function is a function that takes in the states in an action and computes the cost of performing that action as well as the successor state. In other words, it's a function that takes in how the world is right now and then something we do inside that world, and then it returns the cost of doing that thing as well as what the world becomes after we do it. A start state is where we start from, and then a goal test is the test we use to determine if we reached our goal. So let's go back to the problem. A classic search problem is a path problem to find some route between 2 points. Consider a maze represented by an m times n grid, where the objective is to find a path from 0, 0 over here to the top right corner at mn. Describe the problem using the terms of a search problem. Okay, so what are our possible states? We have an n times n grid, and it's a pathing problem, so we're going to be somewhere on this grid. Actually, it tells us we start at 0, 0 right here. But we can be anywhere on this grid, possibly. Like, that is a possible state. And every single state, every single position on the grid is defined by 2 variables. An x, and a y. So this guy is 0, 0. This guy is 2, 2. 0, 1, 2, 0, 1, 2. So now let's look at how we can answer the first question. What are the states of our world? We have a position that can be defined by x and y. So x and y. And x can be anything from 0 all the way to m. And technically, in grid coordinates, it would be m minus 1. If there's m tiles and we start at 0, then there's m. Then the last tile is m minus 1. But we don't have to get too finicky about that. Let's just say 0 all the way to m. Y is similar, except instead of being horizontal, it's vertical, defined by n. So y can be anything from 0 over here all the way to n over here. Let's look at the possible actions. So let's say we're right here. What are our actions? We can, this is a pathing problem, so we can move north, east, south, or west. Don't worry about diagonals because that just complicates things. We're only going to care about Manhattan grid movements. Nice and aligned with the grid. So we can go north, east, south, west. What is our cost? That's a really interesting question because that depends on what we're doing. What we're doing is we're finding a path, not the shortest path. So if we were finding the shortest path from 0, 0 to mn, this would be the shortest path, or anything that like doesn't go on wild detours. Let's look at not the shortest path. This is an awful path. Like, it takes way too many detours to get from our start state to the goal. But based on our requirements, it equally meets the requirement. There's no difference between our squiggly path and the straightforward path. So because we don't have to find the shortest path, we don't need a cost to any of these actions. It doesn't matter if we move extra distance We just have to get there. So our cost for all the actions is 0. A successor function. We'll do this from the book. It's a function that takes in a state in an action. So a state in action, and computes the cost of performing that action, the cost, as well as the successor state. I'm going to swap these around just so the parameters are lined up a little better. And we can actually plug in some details to this function. So our state is our location on the grid. It's the x and y coordinates. Our action is anything from the actions that we talked about. In our successor state, now if you want to drill down really deeply, it could be something like x plus 1 for this east action. But we don't have to get that deep right now. We're just staying conceptual. So we'll just say x prime, y prime, the coordinate that we move to after we move northeast, south, or west. We'll just represent it as x prime and y prime. And then our cost is always 0 because we do not care about finding the shortest path. Start state, bottom left corner. The goal test is our xy positions equals to the goal of going to the top right. I cannot type. Boom. What is the size of the state space for this problem? All that's asking is how many different configurations of x and y, how many different positions on the grid can we be? And that's simple. It's m times n. That's how many tiles there are on this grid. Draw the first 2 layers of the search tree. Okay, I'm going to bring our picture. Ooh, that's not good. Bring our picture over here to help us with reference. So if we start right here, where can we go? We can either go right over here, or we can go up over here. So let's just write that down. Our search tree is going to look like, it starts at 0, 0. That's our start state. And we can either go right to 1, 0, 1, 0, or we can go up to 0, 1, 0, 1 right there. From there, if we went right to 1, 0, where can we go now? Well, on a tree, you don't go back to the parent. That would just be redundant. It would limit the usefulness of a tree. So what we can do is we can either go not left, we can go up or to the right. So if we went to the right node, if we went east first, now we're going to go either north to 1, 1, or east again to 2, 0. Let's connect those nodes. And we'll do it for first move north as well. So here we can either go right or up, but not down and also not left. If we go down, we go to our parent node, back to 0, 0. If we go left, that is an invalid move because we are off the grid. So if we go up, we are at 0, 2. And if we go right, we are at 1, 1. So that's how you draw the layers of a tree. Next up, we have a path problem similar to a map, okay? So it asks us to draw a search tree. So for clarification, it doesn't say in the problem, but we can infer that we're trying to get from A over here, find a route, a path, to F over here. So we're going to start at A. That's our first node. And then we're going to go to the only possible place we can go, which is B. From B, we can follow two vertices or two edges, either to C or D, as you can see over here. Let's connect these nodes. Now from C, we can go to E. That's the only option. Otherwise, we'd be going back to the parents. From D, we can either go to E or G. So E or G. And then from E, notice how C and D, taking the routes through C and D, both end up at E. Even though they're at the same node, they're gonna have different possibilities, because if you land at E through C, you're not gonna go back to C. You could go to D or you go to F. So D or F. But let's say you land at E when you went A, B, D. So you went this route, and now you're at E. You can't go back to D, so D is not an option unlike the other branch, but you can go to C or F. And finally, we have G, which has only one possibility, which is go to the final node, F. So that's our tree. That's our search tree. And one thing to note, it's not shown in this problem because we reached our goal state, F, through the search tree. But let's say we didn't. Let's say we didn't reach F. If we kept expanding this path, A, B, C, E, D, one possibility would be for D to go back to B. So boom, 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 boom. And then we reach a cycle, and depending on our strategy, our search algorithm, we could be in the cycle forever and never complete the problem. So that's just an example of completeness from our reading. But fortunately, we didn't run into that. Let's describe the states. This is pretty straightforward. We have a location on the map that can either be A, B, C, D, E, or F. We can't be at H or J or I because those are not on the map. Those are not possible states. Actions, we can follow edge defined by map. So we can't follow an edge that's not available for my particular location. If I'm at F, I cannot take C to B. That would just not make sense on a map. I could take F to E or F to G. So those are the actions that I can take. And again, just like with the first problem, we do not care about path length. It's not specified in the problem, so our cost is 0. We can take as many detours as we want as long as we get to the end. Successor function, state, action, next state, and cost. So we can start filling these in. Our states is location, so A, B, C, D, E, or F. Our action is follow edge, available edge, and then our successor state is location prime that we reach after we follow an edge, and our cost is always 0. Start state A, goal test, location equals to F. And if you want to be more detailed, you can say location is A. That's at the beginning of our search. So that wraps up our search space handout. Thanks for watching. Good luck in AI.